A warm welcome from Team PharmaCat. Today, friends, I would like to begin with the topic of IR spectroscopy, also called as the infrared spectroscopy. So let us begin with, to study about IR spectroscopy, we should be aware or we should know about the electromagnetic spectrum. So the electromagnetic spectrum of radiation consists of the following. We have the region of the gamma ray, then we have the X-ray region, the ultraviolet region, the visible light region, and then the infrared region and the radio waves region. So the region of interest in today's chapter is the infrared region. So we need to know about the infrared electromagnetic spectrum. So moving on, the region is mainly divided into three types, or basically three regions, called as the near IR region, the middle IR region, and the far IR region. So the region of the IR is expressed in terms of wavelength, having a unit of micrometer, and expressed in terms of wave numbers, having a unit of centimeter inverse. So let us have a look at the near IR region, also called as the overtone region, which has a wavelength ranging from 0.8 to 2.5 and wave numbers ranging from 12,500 to 4,000 centimeter inverse. Next, we have our middle IR region, also called as the vibration rotation region. So the wavelength is 2.5 to 50 micrometer, while the wave numbers range from 4,000 to 200 centimeter inverse. And the third region is the far IR region, also called as the rotation region, which is having a wavelength of 50 to 1000 micrometer and wave numbers ranging from 200 to 10 centimeter inverse. So what is this overtone region, the vibration rotation region, and the rotation region? We will study in detail as we proceed with our presentation. Now, the most widely and practically used region is the middle IR region, having a range from 2.5 to 25, and the wave numbers having a range of 4,000 to 400. So this range of 2.5 to 25 micrometer and 4,000 to 400 centimeter inverse is practically the most widely used IR region for detection in IR spectroscopy. So let us move on to the principle involved in IR spectroscopy, or how the working of the spectroscopy is carried out. So it is a very simple concept which you students need to understand, and I'll explain to you in detail. So what happens is that this IR spectroscopy is mainly dependent on the vibrational and rotational energy of any molecule that has to be analyzed. So in such a scenario, if a frequency of a particular frequency of IR radiation is provided to a molecule which is equal to the natural frequency of the vibration, then the molecule will absorb energy. In simple words, if an IR radiation frequency is provided to the molecule which matches the frequency or which matches the natural frequency of vibration of the molecule, then in such a case the molecule will absorb energy. And after absorbing energy, the molecule will undergo excitation, and this excitation usually occurs when the molecule transitions from the lower energy state level to a higher energy state level. So any molecule which is transitioning from a lower energy state, or also called as the ground state, to a higher energy state, also called as the excited state, then we say that the molecule has experienced excitation. Now, after experienced excitation, the bonds of the molecule will change owing to the dipole moment. And this phenomena is only possible for IR active bonds, or basically molecules which are capable to undergo a change in dipole moment with the presence of an IR radiation. So any molecule given a radiation of a particular IR frequency will undergo a change, that is, the bonds in the molecule will undergo a change in the dipole moment, and because of this the molecule will end up in absorbing energy, and this phenomena will only work for molecules which will react upon the addition or when an IR radiation frequency is supplied to it. So students, moving on to the further principle, when I say that there is going to be a change in the dipole moment. So let us have a quick look at what is this dipole moment. So for any given example of a molecule, in this case, let us consider HCl, that is hydrochloric acid. So when HCl is undergoing, or when HCl is subjected to a particular IR radiation, then the pair of electrons in a covalent bond between the hydrogen and chlorine atoms is dragged more by an electronegative chlorine atom. So the pair of electrons are being dragged away towards the highly electronegative chlorine atom, and because of this electron withdrawing phenomena by the chlorine atom gains a partial negative charge as well as and the hydrogen atom gains a partial positive charge. Hence, HCl possesses a significant dipole moment. So when atoms vibrate along a bond or rotate about a bond, regular fluctuations in the dipole moment occurs, and this fluctuation in the dipole moment produces an electric field which propagates in the form of waves. The rotation of these waves hence equals the natural frequency of vibration or the rotation of the atoms. So basically in IR spectroscopy, the changes in the vibrational energy will depend upon, namely, first is the mass of the atoms that is present in the molecule, second, the strength of the bonds, third, arrangement of atoms within the molecule. No two compounds will have a similar IR spectra. This is a unique trait of the IR spectroscopy. No two compounds will have similar IR spectra until and unless those compounds are enantiomers to each other. So only compounds or in having their respective enantiomers, or only compounds which are enantiomers will have a similar IR spectra. Other than that, every molecule will have its own unique IR spectra. So moving on to the theory of IR spectroscopy, a typical IR spectra basically consists of three types of absorption bands. So there are three main types. First is the fundamental band, then we have the overtone bands and the combinational bands. So students, let us have a look at the fundamental bands. So what are fundamental bands? Basically, fundamental bands, as you can see in this diagram or the spectra. So basically a typical IR spectra will be a graph of the transmittance, that is person transmittance versus the wave number. Now unlike any UV spectra, you can see that you are getting the spectrum as an inverted peak in the spectra. Why is it so? Because we are plotting transmittance on the y-axis. So basically transmittance is the reverse of absorbance. So that is the reason why we are getting these types of inverted peaks in our IR spectra. So IR spectroscopy basically deals with the uh, person transmittance on the y-axis, whereas on the x-axis we have the wave numbers. So here you can see we have the fundamental bands here and we have the overtone bands here. So let us have a look at the fundamental bands. So as you can see, the fundamental band is typically in any IR spectra will appear as the most or higher intensity peak on the spectra. So compared to the other peaks, a fundamental band will always have a higher intensity as compared to overtone or combinational bands. So when does the fundamental band arise? Usually when a molecule is transitioned from the ground state to the one and only excitation state, then the resulting spectra occurs in the form of a fundamental band. And in case of overtone bands, when the transition occurs from the ground state to a number of excitation states, that is when the number of excitations is more than one, that is the molecule can be excited from the ground state 0 to an excitation state 1 or 2 or 3. In such a case, you get overtone bands, and because of this, because of the multiple excitations that the molecule undergoes, the overtone bands usually occur as a smaller peak at higher wave numbers. So basically you can see that the fundamental bands usually occur at lower wave number values, while the overtone bands usually occur at higher wave number values. Now let us have a look at combination bands. So basically, in the case of combination bands, when more than two or more fundamental vibrations are excited simultaneously. Now in this spectra, you can see that there are multiple high intensity peaks clubbed or grouped together in the spectra. So basically, these are the combination bands of in the IR spectra. So these combinations are basically arising when more than two fundamental vibrations occur simultaneously. So let us move on to a phenomena called as the Fermi resonance. So when does a Fermi resonance occur? As the name suggests, resonance, that is transition from the lower energy state to higher energy state. So basically when there is an interaction which will occur between fundamental overtone or combinational bands, then such a phenomena will be called as a Fermi resonance. So usually what happens, as you can see here, in this typical spectra, we have a fundamental band, which is the band having a higher intensity, and then next we have an overtone band. So basically what happens in the Fermi resonance is that usually when two fundamental or one overtone band, as you can see in this example, have the same energy. So basically, when one overtone and one fundamental band are having the same energy, in such a case, the molecules transfer its energy from fundamental to overtone and from overtone back again to fundamental. So because of this, the levels become partially, that is the spectra is having partial fundamental or partial overtone bands. So that is why one fundamental band is gaining partial overtone band, and a overtone band is gaining partial fundamental band spectra. As a result of this, two strong bands are observed in the spectrum instead of one strong and one weak band. So in this case, instead of one strong and one weak band, we are getting two strong bands, which is called as the Fermi resonance. So let us have a look at the fingerprint region. Now basically the fingerprint region is the IR region which is existing below 1500 centimeter inverse. As you can see, I have drawn a red block around the fingerprint region. Now, what is the significance of this fingerprint region? So basically, this fingerprint region is rich in many different absorption bands. And that is why mostly the combinational bands exist in the fingerprint region. So basically here the bending vibrations are greater than the stretching vibrations, and any small difference in structure or constitution of a molecule will result in very significant changes in absorption bands. So that is why this fingerprint region is very useful for detecting slight changes in the molecule. So any slight change in the structure or the orientation of the molecule will give us strong bands in the fingerprint region. Many compounds show unique absorption bands in this region, which is very useful for identification of various compounds, basically the alcohols, esters, lactones, acid anhydrides, then the tertiary groups, then cis transalkenes, as well as it can also help in identifying whether the compound is monosubstituted or disubstituted, or whether any functional group is located in the ortho, meta, or para substitution. So that is why the fingerprint region is very important in detecting the various functional groups in IR spectroscopy. So basically, the fingerprint region is divided in three types. One region ranges from 1500 to 1350 centimeter. The second region ranges from 1350 to 1000 centimeter inverse, while the third ranges below 1000 centimeter inverse. So each functional group will have an unique absorption band in one of these various three fingerprint regions. So any molecule which is existing in one of the three fingerprint regions, then suppose we are getting an absorption band in the first or the second region, then we are able to accurately identify the nature of the molecule, whether it is an alcohol, acid, ester, whether it is disubstituted, monosubstituted, or if the substitution is present in the ortho, meta, or para position. So let us have a look at the various vibrations that occur when a molecule is subjected to IR radiation. So whenever a molecule is subjected to IR radiation, the atoms of the molecule are never stationary, but they keep on fluctuating continuously due to different types of vibrations. So these fluctuations or vibrations can be of the varying types as below. So basically we have two types of vibrations. One primary type is the stretching vibration. In this stretching vibration, what happens basically is that the bond length will either increase or decrease. So whenever the bond length of an atom or a molecule is increasing or decreasing, we say that it is undergoing a stretching vibration. And stretching vibrations can be of two types, symmetric and asymmetric. Next, second important primary type of vibration is the bending vibration. So basically in the bending vibrations, there is a change in bond angle occurring. So basically in this vibration, there is no change in bond length, but there is a change in the bond angle, and especially the change in the bond angle occurs between bonds usually with common atoms, or basically in this kind of vibrations the movement of groups of atoms occur, and that is why the name bending. So bending vibrations are basically of the following types. First we have the scissoring, second we have the rocking, third the wigging or the wagging, and fourth is the twisting vibrations. So let us have a look at each of these vibrations and how they are. As you can see, in a symmetrical stretching, the bond length decreases or increases symmetrically in the same direction. As you can see, the bond length is decreasing or increasing in the same direction. That is why the symmetrical decrease or increase in the bond length is called as the symmetrical stretching. Next, we have the asymmetrical stretching. So usually in asymmetrical stretch, length of one bond will decrease while the length of the other bond will increase. So when such type of stretching is occurring where one bond length is decreasing and the other bond length is increasing, it is termed as asymmetrical stretching. And let us have a look at scissoring and wagging. So basically scissoring and wagging are also called as in-plane bending vibrations. Why? Because they occur in the same plane. So usually in scissoring, bond angle decreases. As you can see, the angle, this bond angle is decreasing, and the movement of the vibration is basically in the form of a scissor, and hence it is called as scissoring vibrations. In rocking type of vibrations, as you can see here, bond angle is maintained. That is, there is no increase or decrease in the bond angle, but you can see that two bonds bend to the right simultaneously, and next moment bend to the left simultaneously. So basically what is happening is that two bonds are bending either on the right in this manner, as you can see my laser, or they will bend to the left direction in this manner. So such type of bending is called as rocking. Next, we have the above the plane type of stretchings or the out of plane type of stretchings. So basically what is happening in the out of plane bending is that first we have is the wagging, where both the atoms move to one side of the plane. As you can see, both these atoms are moving on the same side of the plane. That is why they are both signified as the plus sign. And such type of stretching is called as the wagging stretching. Now in twisting type of stretching, one atom is above the plane and the other is below the plane. So the atom that is above the plane is signified with a plus sign, while the atom that is moving or stretching below the plane is signified with a negative sign. So this kind of stretching is called as the twisting vibrations. And wagging and twisting are type of out of plane bending vibrations, because as you can see in wagging, both the atoms are bending above the plane, while in twisting, one bond is bending above the plane while the other bond is bending or to below the plane. Now let us have a look at the molecule of carbon dioxide. As you can see, carbon dioxide is one of the type of molecules which is capable of undergoing multiple stretches. So as you can see in the first diagram, carbon dioxide is capable of undergoing a symmetric stretch wherein the bonds existing between the carbon and the oxygen atom are able to increase or decrease in the same direction. That is, they are able to increase or decrease symmetrically. So they also exhibit a symmetric type of stretch. While you can see in the second diagram is an example of how carbon dioxide can also undergo asymmetric type of stretching, where one of the bonds associated between the carbon and oxygen may increase in length while the other bond might decrease in length. So because of the increase and decrease, they are capable of moving the length, that is the bond length is capable of increasing or decreasing asymmetrically. So they are able to undergo asymmetric stretch as well as carbon dioxide is capable of undergoing bending type of vibrations as well. It could be in plane type of vibrations or it can also be an out of the plane type of bending vibrations. So now just as with the example of carbon dioxide, there are many molecules or compounds which are capable of undergoing multiple stretches. So depending upon the multiple stretches that any molecule is or multiple stretches that are occurring in the molecule, we are able to depict it from the IR spectra, as in because owing to the different types of stretches, we will get different types of bands in our IR spectra occurring over a variable range of our wave numbers. So depending upon the wave numbers and the bands, we are able to understand what type of functional group or what type of molecule or atom is present in our sample or analyte, which is to be analyzed using the IR spectroscopy technique. So in this lecture, we have studied about the basic theory principle of IR spectroscopy as well as the number of stretches that a compound or molecule is capable of undergoing. So that is all for today's lecture. In the next lecture, we'll study about the instrumentation of IR spectroscopy as well as its applications. Thank you.